Example: use Newton's method to approximate the solution of the equation x cubed minus 3x minus 6 equals 0, accurate to 2 decimal points. As we saw before, we don't want to choose the first one to be 1, but x equals 2 is a good choice for the first value of the x. So x1 equals 2. Because we are going to use this more than one time, we would like to evaluate that. So we evaluate f of x over the derivative of f of x. And we try to simplify if possible. In this case, it is impossible, so we will have to leave it like this. The method saying that if I want to find the next x, then I just have to take the previous one minus f of x over f prime x and replace x by the previous value of the x, which is xn minus 1. Let's find the next one, which means x2 when x1 equals 2. We plug 2 into the expression of x sub n equals, and using calculator we get that this is about 2.444. And now we will plug this again into the equation to find the next value of the x, and we get more or less 2.35915. We'll do it again. And we get roughly 2.35553. Now we notice that the difference between x3 and x4 is only in the third decimal. But because the two decimals are the same, the approximated solution is accurate enough. Newton's method is a numerical method. It means that the machine can do it really fast. The machine first will guess 0 and we'll call it x1. Then it will put this into this expression and we'll calculate that. In our case, we are going to do this using a calculator. And it will spit out the new number and it's going to check for accuracy, which means is the difference between two consecutive values of x is small enough. Or we can check if two consecutive x's are having the identical required decimal. If the answer is yes, we are done, and the last x is the approximated 0. If it is no, then the machine or we are going to repeat the process as many times as we need. This is kind of a flowchart, and if you know how to program, you can make a little program into your computer and it's just going to evaluate everything for you. Example: approximate one solution of the equation x cubed minus 4x minus 1 equals to 0, accurate to 2 decimal places. First, I'm guessing some 0 of this equation. For example, I plug in 0 and I get negative 1, which is not bad because negative 1, from there I can get somehow to the 0. So I'm going to take the first one to be 0. Now we are going to evaluate f of x and to differentiate the function to find expression for the next value of the x. In this case, we get this expression, x n plus 1 as a function of x n. And in our case, we are going to find x2 by substituting, xn, which is x1 in this case, equals to 0, and we get that. And we get negative 0.25. Now we are going to check if this is accurate enough. Because this is not accurate enough, we will have to repeat the process. So the next step, we are going to find x3. We are now substituting x2 in the expression to get x3, and we get that. Using calculator, we get negative 0.254. Again, we have to check if this is accurate enough. Accuracy to 2 decimal places, it means that the difference between the two is in the third decimal. As you can see here, the difference is indeed in the third decimal, and they have the same 2 first decimals, which means they are accurate for 2 decimal places. Because the answer is yes, we conclude that this is a good approximation. Please note that there may be more zeros to this equation because it's a cubic equation. We don't know. But now we found at least approximation of at least one of the zeros. Example, approximate the fifth root of 8 accurate to 1 decimal place. Finding the fifth root of 8 is like finding the solution of the equation x to the 5 equals 8, or the zero of the function f of x equals x to the 5 minus 8. Because Newton's method can find zeros of functions, we are going to apply that. We notice that f of 1 is less than 0 and f of 2 is more than 0. The function is a polynomial, which means it is a continuous function. And we also see that it changes sign on the interval between 1 and 2. It means that the fifth root of 8 is between 1 and 2. So it's okay to start with the first value of x, x1, to be 1. To get the expression for the next x's, we need to do some evaluations here. And we get that. x2 is x1 minus x1 to the 5th minus 8 over 5 times x1 to the 4. x1 is 1. We substitute 1 and we get 2.4. Now we are going to substitute in the expression 2.4 and we will use calculator, and we get that the value of x3 is approximated by 1.968. As you can see, this is not accurate enough. So we need to find x4. We repeat on the process and we get this one. Again, this is not accurate enough because you can see that x3 and x4 do not have the same decimal, the first one. So we have to continue and evaluate x5. And again, x5 and x4 do not have the same first decimal, so we have to continue. But here is x6. You can see now that x5 and x6 have the same first decimal, it's 5, and we can stop. We can conclude then that the fifth root of 8 can be approximated by 1.516.